Hello, this is lecture 17 where we're going to talk about caches and memory hierarchy. So as you may notice, there is a switch in the instructors. I will be taking over from Professor Bill Author. I'm Satish Narayanaswamy. I will be handling two topics, caches and virtual memory. I plan to release an introductory video about myself and the research I do, etc. Please look out for that. I intend to follow the same schedule that Bill has been following with respect to the asynchronous lectures. So I would have the same set of office hours every week, and also look out for the lectures on the Google Drive and the Media Gallery. I may also release it on YouTube in addition. Also, there would be a quiz every week. So the only difference might be that I intend to produce a few shorter videos so that it's easier for students to digest the material. I would also be releasing a full-length video that includes all the topics, so that way it's easier for you to process the information if you want to go through it in one go. But having those smaller lectures hopefully gives you a chance to revisit some of those challenging topics and understand them in a better way. So there are two upcoming deadlines. One is for homework 4, which is going to be due in about 10 days. You may have noticed that we changed the homework policy on collaboration. So we want to give you the option to collaborate with your peers to solve the problems, and we are hoping that this would not only reduce some of the workload that you have, but also enhance learning, because collaborations can lead to better understanding of concepts. Project 3 is due in a couple of weeks. If you have not already started, please do so. It's a very important part of the course, so you don't want to delay that. All right, so let's get started. What is a memory system? If we go back to our pipeline data path, you will see that we've already talked about two different types of memory. One is a register file, which is kind of small. It had space only for 8 words worth of data. And then we had instruction memory and data memory. They are an abstract representation of a memory system. I say they are an abstract representation because a memory system in a real computer is much more complex, as it is made of several different types of memory devices. For example, your laptop has probably 3 to 4 different types of memory technologies. So now the question is, why do we need to think about so many different types of memory devices, and what do we need them for? Well, we need memory system to store data. An LC2K program, for example, a program written for the LC2K ISA, can access 2 to the power of 18 bytes of data. That's not a lot, but if you look at MIPS program, which is based off MIPS 32-bit ISA, it can access about 2 to the power 32 bytes of data. That's about 4 gigabytes. So that's something. But then if you take a modern ISA like an ARM64 or x86-64, which are both 64-bit ISAs, a program can access 2 to the power 64 bytes of memory. Now that's a lot. That's 18 billion bytes worth of data. The problem is no single memory technology is both fast and big enough to store all of a program's data, especially the ones that are written in modern 64-bit ISA. So our goal is understand the principles behind designing a memory system that is fast, big, and cheap to store a program's data. Now, before we can understand the different memory technologies and construct a memory system, it's worthwhile to think about what properties we can use to reason about these different technologies. Space is obviously an important consideration. Speed is next. We want a memory system to be fast so that if we have a load instruction, it can retrieve the data fast so that it wouldn't stall the data path. We also would like the memory system to be cheap so that your computers are affordable. We also think about a property that allows memory systems to persist data when the power is turned off. We'll see how some of the memory technologies can persist. They're called non-volatile memory systems, and the ones that cannot persist are called volatile memory systems. Now I can take these properties and construct what I call a memory pyramid. A memory pyramid is organized such that the fast devices are placed on the top of the pyramid and the slower devices are placed at the bottom of the pyramid. The top of the pyramid, the fast devices, they're also expensive. And so we cannot afford a lot of them. And so therefore their size tends to be smaller. The ones at the bottom of the pyramid, their cost tends to be cheaper and therefore their size can be much larger. Now you see that there are different types of technologies mentioned along these three boxes. So let me go through each one of them very briefly so that we can understand their properties a little bit better. The first one is a static RAM, which sits at the top of the pyramid. It's really fast, but it is expensive. It takes about 6 transistors per bit, typically used within a processor chip. They can range from a few kilobytes to a few megabytes, and the latency can vary from 2 nanoseconds to a few tenths of nanoseconds depending on the size. And they're expensive. You can probably store an LC2K program's data entirely on an SRAM chip today, but you certainly can't do that for an ARM64 program, as it would take an exorbitant amount of cost to do that. SRAMs also tend to be volatile, meaning if you turn off the power, the data stored in SRAM would disappear. The next technology is dynamic RAM. It sits in the middle of the pyramid. It's much more cost efficient than SRAM, but it's also slower. It can come in sizes of about tens of gigabytes today, but the time to access any data tends to be about 100 times slower than an SRAM access. But they are cheaper, but still not cheap enough to store all of ARM64's program data. And like SRAM, they are also volatile. Next, we have disks. These are made of magnetic hard disks and they have mechanical elements in them. And as a result, they're super slow. They're 100 times slower than DRAM. And remember, DRAM is 100 times slower than SRAM. So we are talking about 10,000 times or more slower than an SRAM. But they can be much larger, tens of terabytes, and they can probably store most programs' data, but not the maximum amount of data that you can access from an ARM64. It's still expensive, and we'll see how to mitigate this later. The other advantage of disks besides cost is that it's non-volatile, meaning you can turn off the power and still have the data persistent. So this is the place where you would typically store your files, like your images, videos, programs, etc. A newer technology that has made it into our commercial computers is flash drives. They're also called, they're an example of a solid state disks. They're increasingly replacing hard disks in our computing systems. For example, today mobile phones and laptops do not have hard disks, and they only have solid state drives. They sit in between DRAM and disks in terms of cost and performance. They are still slower than DRAM. They're still slower than DRAM, about 2 to 3 times, but they're as big as a hard disk. They can store today up to a few terabytes worth of data. And so, because of these desirable properties, we see this trend shifting towards SSDs in our systems. Still not cost efficient to store ARM64's data. And like disks, they're non volatile, and hence they're a good competitor for hard disks. Here is a summary of all the technologies we talked about. So at the top of the pyramid, you have static RAM, dynamic RAM in the middle, and then you have a bunch of solutions for non-volatile systems. We talked about solid state disks and hard disks, but you can also think about DVDs and magnetic tapes, which are even more larger in size and more cost efficient. There are newer technologies like DNA storage, which researchers are looking into to make it easier to store even more amount of data, but they also tend to be much more slower than even magnetic tapes. So what do we desire? Well, we want a memory system that is as fast as SRAM that sits at the top of the pyramid, but we also have space to store all the data that we want. And so we need a system that is big and cheap, like a hard disk. So we want the best of both worlds. How to achieve that? So to understand how to construct a memory hierarchy, it's worthwhile to think about an analogy from our life. Say you are an avid book reader that uses the library a lot. So a library is a place that is big enough to store all the books that you ever want to read. But it takes a few hours to go to the library and fetch a book. So what do? Well, maybe you borrow 20 books or so and keep them on your bookshelf at home. And whenever you need to read a book, you go to the bookshelf. It may take a few minutes. It's still a little bit of a hassle because maybe if you are at school or if you're traveling, then it's a little bit harder to get to those books. So the solution is to have a backpack to store maybe 2 or 3 books that you're reading at the moment, which you can reach into in a few seconds. So this sort of illustrates the idea that I want to use to build a memory hierarchy. Each of these different storage devices, library, bookshelf, and backpack, each serve a purpose. It's not like one is better than the other per se. I need all three of them to have the option to store all the books that I ever want, and at the same time have a solution for me to keep my book that I'm reading and reach to it very quickly. And if you think about a memory system, it's very much like the book example. You have caches, which is similar to your backpack, which is fast and kind of expensive, and so you can have only some data in it. And then you have your main memory made of DRAM, which is sort of like your bookshelf at home. It is a little bit slower, but much bigger than your backpack or cache. And then you have your disk, which is similar to your library that pretty much stores all the data that you ever want your program to access. Now, in order to get the benefit of cache's performance, what we typically try to do is exploit the behavior of a program where we see that most programs, they exhibit what's called as a locality of reference. We'll learn more about that later today, but essentially it allows cache to service most of the loads and stores, thereby making the whole system appear to be as fast as this fast device. And once in a while, you reach out to the DRAM and you reach out to the disk when you need to get that rare data. And you bring it back and store it in the cache so that you get to use it in the future. So this is the realistic memory hierarchy now. We also have caches, which is used within the processor, and this is on chip. The main memory is off chip because it's outside your main processor. It sits in a different chip. And your swap space, again, it's your hard disk. And it's used to store any data that spills over from memory. Now, what I have not answered so far is even hard disk, we said, is too expensive to store 18 billion bytes of data because it would take almost $1 billion if you try to do that. So what's the solution? Well, we are going to fake it. We are going to construct a computing system that promises to the programmer that the programmer can access 2 to the power 64 bytes of data, but we are really not going to have space to store that much amount of data. And the hope is that the programmer will never want to access that much amount of data. Once in a while, that trick fails. And if it does, then you get a window like this, which you may have seen, where the computer complains that your program has exceeded the machine's available swap space on disk. That's why when you buy software, typically they recommend a particular size for your main memory and your hard disk for you to be able to install it. So later on, a few lectures later, we will be tackling this problem under the concept called virtual memory. Now, the memory hierarchy that we talked about is fairly complex. It has several devices, caches, main memory, disk, and it has different latency and size considerations. We don't want to expose these details to the programmer because otherwise programming can become a much more tedious job than it is today. So the solution is the ISA abstracts away all these details away and makes them invisible to the programmer. The only thing the programmer gets to know is the specification of the ISA about how many different types of memory locations they can access. So a 64-bit ISA says a programmer can access 2 to the power 64-bit locations. But the details of the size of caches and main memory and disk, etc., are hidden from the programmer. The view that the programmer gets to see of the underlying hardware is called the architectural view of the memory. The cache is an important part of the memory hierarchy, and we will be spending a fair amount of time understanding its architecture and performance. The term cache commonly refers to SRAM device used within the chip. However, even a DRAM can be thought of as a cache in that it temporarily stores data fetched from a hard disk. But in this course, when we talk about caches, we are referring to SRAM used within the processor chip. So what is a cache? Well, a cache is used to store data that is most likely to be referenced by a program in the future. Our goal is to try to maximize the number of loads and stores that are serviced by our fast cache and avoid going to the slow main memory. And in the process, we are going to try and improve this metric, which we're going to call as the average memory access time or latency of a store or load. I will define this metric a bit later, but it's a performance metric that we're going to use to reason about a cache's performance. So why are caches important for us to understand? For one, if you look at a modern processor, much of its area is devoted to cache. Nearly more than 2/3 of a processor's die is consumed by caches. Even if you're not a hardware designer, it is important to understand caches because it has a significant impact on the performance of your program. So here is a simple example that illustrates the importance of cache on program's performance. They both have the same functionality and they differ only very marginally, the order of the subscripts in the array access. yet their performance vary by an order of magnitude. So if you go back to the lecture one, Professor Arthur had explained the differences and did a live demo. I encourage you to take a look. We will also be coming back to this example later on when we talk about spatial locality, which would help us understand the reasons even more in depth. Let's design a very simple cache architecture. Let's start with a very simple index memory. It has space for storing 4 data items. Now let's also assume that the address space also has only 4 addresses. So now I can map those 4 addresses as follows: 0, 1, 2, 3. And now given an address, I can use a simple decoder to select one of these 4 locations and retrieve my data. Now let's make it a little bit more complicated. Instead of 4 address locations, I'm going to assume that my program can access 32 address locations. But my memory has only 4 data items, space for 4 data items. So now I have to treat this like a cache. Now the question is how to map the 32 addresses to 4 locations. And how do I know which of these 32 locations I have cached? To solve this problem, we need one more array. Okay, now I have created one more array. I'm going to call that as a tag array. The original memory, I'm going to call that as a data array. Even though I'm going to call them as arrays, these are hardware structures. Now, when I cache address, I can note down the address location in my tag array. So let's say I access the location 31. I note down the address and then store the data corresponding to that address in the tag array, in the data array. And I can continue this process. Let's say I access an address 10, then 20, and then let's say 0. I would have their corresponding data in my data array. And let's say I have a address that I want to access. Let's say the address is 10. How do I know which row contains my data? Well, I need to take this address and compare that address to each of these tags. If the tag matches the given address, then I know that I found the data that I was looking for. Now this is what we're going to refer to as a cache hit. I was able to find the data of an address that I was looking for. Now the question is, what type of a hardware structure would allow us to perform so many comparisons in parallel? So the hardware structure that supports this functionality is called the Content Addressable Memory, or shortly CAM. CAM is a very simple structure. It has the ability to store a set of data items, and given a key, it would compare to all the data items and then tell us whether it found a match or not, and if so, which entry found a match, which is exactly what we explained as a tag array. So the hardware for CAM looks something like what I have shown in the picture here. You have the key that is given as search data at the bottom, and you have the data items, or in our case it would be the tags that are stored in each of these rows. So in order to perform a comparison in parallel to all of these rows, I would drive these vertical lines that you see in the picture with the bits in the search key. And the little dots that you see here are the ones that implement the comparison functionality, in the sense that if the given bit matches with that of the stored bit, it would raise the signal in the line that is connected to it. And the end result is that if all of the bits that are stored in a given row matches with that of the given bits in the key, then that entry would be enabled. And that's how we can discover which entry contains the data that matches the key that is given. So we have used CAM in the past. So if you go back to our data path with the branch predictor, so think about the branch target buffer. So if you recollect, a branch target buffer is one that stores the program counter of the branches. And when you see a new branch, you take the program counter value, and then you want to search all the entries in the branch target buffer and see if that branch exists in the branch target buffer. And if it does, then you fetch the target, and if your predictor says taken, then you jump to that target. So the structure that we would use to implement a branch target buffer is also a CAM. Now let's get back to our cache design. So we have two arrays, tag array and a data array. The tag array is implemented using CAM. Now let's briefly understand how this cache would work. If I provide an address, let's say 10, I would first look up the CAM and see which entry matches. And there would be no more than one entry that would match. And then I would know the entry in the data array that I should be accessing. And so then I would retrieve the data and then send that data back to the processor so that a load or a store can use that information. Now let's say instead of 10, I provide an address, let's say 7. You would again look up the tag array, and you will discover that 7 is not present in any of the rows. Now that would be called a cache miss. In the case of a cache miss, you wouldn't find the data for the address that you're looking for, and therefore you would have to go to the next level of the memory hierarchy, typically the main memory. Now when you do go to the main memory, you would fetch the data corresponding to the address 7, and you would want to bring it back into the processor and store it in your cache. But we have a problem. Our cache is already full, and so there is no place for another data item. So therefore we have to pick a victim and evict the address that is chosen as a victim out of the cache and replace that with the new address 7. We have, obviously in this example, we have 4 choices. Now the question is, out of these 4, which one would you select as a victim? Now that is informed by what's called as a replacement policy of the cache. So the question is, how do I design my replacement policy? To understand that, we have to understand a concept called temporal locality. So what is temporal locality, and how can it help us implement a replacement policy for a cache? So to understand that, let's go back to the cache example that we used before. So I have a tag array and a data array populated with 4 addresses. Now let's take a look at the address pattern that may have resulted in this cache state. maybe I access 31, then 10, 20, and 0. Now let me continue this a little bit more. 10, 20, 0, 20, 0, 20, 0. Now let's say I end up with a new address, let's say 7. Now the address 7 is not present in the cache, so it would be a cache miss, so I would go to the main memory and get the data. Now I need to find space for this address 7 in my cache. The question is, which address do I pick as a victim and evict it? Try to pause the video here and try to see if you can come up with a good guess for which address might be a good candidate as a victim. If you pick 31, that is a very good guess. Well, why does it make sense? Well, what you're intuitively using is this idea of a temporal locality. So what temporal locality means is if I access an address now, that address has a very high chance of being accessed in the near future compared to all the other addresses. So by that principle, I could argue that at this point, when I had to find a victim for the address 7, among the 4 choices I had, 0 had the highest chance of getting accessed in the future, followed by the address 20, and then followed by the address 10, followed by the address 4. So address 31 happened to be the least recently used address, and therefore, according to temporal locality, it had the least chance of being accessed in the near future compared to the rest of the 3 addresses. So I would pick 31 as a victim, evict it from the cache, and replace it with address 7 and its data. Now let's say I get another new address 8. Now 31 is out of the cache, so it is out of the picture. Now these numbers would change after I have brought in 7. So 7 would be the most recently used address, 0 would be the second most recently used address, 20 would be the third most recently used address, and now 10 would be the least recently used address, and therefore I would have to pick 10 as a victim and replace it with the address 8. Alright, so to formalize the notion of temporal locality, we can look at the precise definition of it. It essentially says that if you access a memory location, let's say 1000, you're more likely to re-access that location than you will be to reference any other random location. So according to this principle, if I access any new location that is not there in the cache, meaning the address is a miss in the cache, then temporal locality mandates that I evict some candidate from the cache and allocate this address that I just missed in the cache. And we also talked about the idea of a LRU, which is essentially that in order to realize the temporal locality, I should design a replacement policy which always picks the least recently referenced or least recently used cache block and evict that to make space for the new line. Is LRU an optimal replacement policy? Answer is clearly no. It's just a heuristic that works in the common case, but there can always be some program for which LRU is not the best replacement policy. Now the question is there anything like an optimal replacement policy? Well, unfortunately no, because we really don't know what a given program can access in the near future. If you can have the exact sequence of memory accesses that a program is going to make, then it is possible to design an optimal replacement policy. But unfortunately, in the real world, it's often impossible to predict exactly what sequence of addresses that a program would access going forward. As a result, there is no optimal replacement policy, and so we have to think about heuristics such as LRU to design a replacement policy. I would like to illustrate the function of a cache by simulating a very simple cache architecture that has two cache lines, 1, 2, and it has a tag field that is of size 4 bits. And the reason why this is 4 bits is because my address space has 16 addresses. So log2 of 16 is 4. And each address I can access 1 byte of data, so therefore the data size is 1 byte. I also have 2 more bits, 1 per cache line, that tell me whether or not the cache line is valid. And I have a very simple program on the left hand side that I'm going to execute and observe how the cache functions. I also have 4 registers which these load instructions are going to load values into. So load instruction, the first load instruction reads from the location 1. Is it in the cache? Well, if there are no valid tags, both of them are invalid, which means that there is no valid address 1 in the cache, and therefore it is a cache miss. Therefore I need to go and fetch the data from memory and allocate space for this address in the cache. I have enough space in the cache because there are these invalid bits. I can pick any one of those two. I'm going to pick the first one and populate that cache line with the address 1 and its data. And then I would return the value 110 to the processor so that the processor can write the data into its register R1, which is the register that you're trying to load into. Now I would also set the least recently used bit so that when I end up filling up the cache, I would know which cache line to evict. At the moment I have accessed only one cache line, so the other one is the least recently used cache line. Let me go ahead and execute the next instruction. So I'm also going to keep track of how many misses and hits I'm going to be observing. So far we accessed 1 memory location and that is a miss, so 1 miss and 0 hits. Let me go ahead and execute the second load instruction. It is accessing the location 5. I'm going to compare 5 with all the tags. There's only one tag and that doesn't match, and therefore it is a cache miss, which means I need to allocate space for it. Fortunately, I do have a cache line which is empty, and so I'm going to use that for storing the address 5, fetch the data from memory and store it in the cache and return it to the processor, which would then store it in the register R2. So now I have 2 misses and 0 hits so far. Let me I would also need to update my LRU bit. Before, the second line was the LRU, but now because I have just accessed this line, the other one becomes the least recently used line. Let me go ahead and execute the third load instruction. It accesses the location 1. I check the tags. 5 doesn't match, but the tag 1 does match, and we have our first hit, which means that I don't have to go to the memory, and instead I can return the data from the cache itself. Therefore now we have our first hit. Keep in mind that we have to update the LRU. Now that I have accessed the address 1, this cache line, the other one becomes the least recently used cache line. Now I'm going to access the cache with the third address 7, which I've never accessed before, and so when I try to look it up, the cache doesn't have that tag, and so both of them mismatch and then indicates that it's a cache miss. Now I need to allocate space for this address 7, and according to temporal locality, we are using the replacement policy based on LRU, where I want to evict the least recently used cache line, which we've been diligently keeping track of. So it happens to be the case that 5 is the least recently used cache line. So if you go back in time, you will see that 1, I just used it, so that is not the least recently used cache line. And if you go back, 5 happens to be more older than 1, and therefore that must be evicted. So I would evict the address 5, replace it with the address 7, and bring the data for 7 from memory, overwrite the data with the new data, and return the value to the processor and update the register file. Unfortunately, we have encountered one more miss, so we have 3 misses and 1 hit so far. The final instruction I'm going to go and execute, which is also addressed to 7, and in this case, of course, it's going to be a hit because we just accessed it and it's there in the cache and the tag matches, and we would just return the value 170 to the processor. You'll notice that this load is loading to a different register, and that's why you see 170 in 2 different spots in the register file. Just like how we had defined performance metrics like CPI and execution time for the data paths, we would like to define a metric to measure the performance of a memory subsystem. So the metric that we're going to use is called the average memory access time, or AMAT. So the memory access time is the time that a load or a store instruction takes to retrieve data from memory, wherever it is. It could be in the cache, it could be in the main memory, or it could be in the disk. So for a given load or a store, you can ask the question, how long does it take for me to get the data from the memory hierarchy? Now, if you compute that time for every single load and store instruction in your program, and then you take the average of all that, what you get is average memory access time. So it tells us on an average how long a given load or a store instruction would take. And we would like this latency to be as close as possible to cache's latency. And that would be true if majority of loads and stores are serviced by the cache. So there are several ways in which we could compute average memory access time. One very naive method to do it would be to compute the time for every single load and store, and then you take a simple average. So for example, if you go back to the illustration that we did for a simple cache architecture, we observed that we had 3 misses and 2 hits because we had 5 load instructions. And let's say we make some assumptions about how long the cache would take to access. Let's say it's 1 cycle, which is a fairly realistic assumption. And let's say that main memory would take 15 cycles. Now that's a little bit unrealistic because typically it takes much longer than that, maybe 100 or even 200 cycles. And I'm also going to assume that this time includes the time I'm going to spend in checking whether it's a cache hit or a miss. And keep in mind that I first have to check the cache, and if it is a miss, then I go to the memory. So if you look at the problems, this assumption could be stated in a few different ways, so you have to be a bit careful about how you process this information. Alright, so now I have this information. I could then go and compute the AMAT for this very simple program with 5 load instructions and a cache hierarchy. What I could do is I could say, well, 3 are misses, so each one of them would consume 15 cycles. 2 of them are hits, and each one of them would consume 1 cycle. Add them all up, I would get a number, divide them by 5, then I would get AMAT. Another way to do it would be to use this formula that is given to us here. What it says is AMAT can be computed as the cache latency, which is 1 cycle in our example, times the hit rate, meaning what fraction of the memory accesses hit the cache. So that fraction of memory accesses would have to incur only the cache latency. For the remaining fraction of memory accesses, I would have to incur the latency of memory, which is 15 cycles. So I plug all these numbers in, I get 1 cycle for the cache latency. The cache hit rate for our example is 2 hits divided by 5 total accesses. And then I have to sum it up with 3 out of 5 times I have to go to the main memory, and that takes me 15 cycles, including the time it takes to check the cache hit or miss. And so I add them all up and I get 9.4 cycles per reference. Let's take another problem and apply the similar principles and compute the average memory access time. So in this example, we also have a disk. So I would go from cache. If it's a miss, I go to memory, main memory, and then if it is a miss in main memory, I go to disk. We didn't really talk much about how main memory is architected, but that's not essential to understand how to compute AMAT for this memory hierarchy here. And just like in the previous example, I'm going to assume that the main memory latency includes the time it takes to determine cache or miss, and also the disk latency includes the time it takes to check the main memory and the cache. I'm also going to make some assumptions about a program. I'm going to assume the program has 100 memory references and the cache hit rate is 90%, and that main memory hit rate is 80%. So then the average memory access time could be computed as the following. So 90% of all memory accesses hit the cache, and therefore they incur only 1 cycle penalty. Now 10% of memory accesses have to go to main memory, so they would incur 0.1 times 100 cycles. Now of the 10%, some fraction of them would have to go to the disk, and that fraction is defined by the miss rate in main memory. So that would be, miss rate is computed as 1 minus 80%, so that would be 20%, so that's 0.2 times the time it takes to access the disk, that is 10,000. So if you compute this equation, then you get the answer. Alright, so now if you think about how to reduce the average memory access time, and the reason why we want to reduce it is so that we can improve the performance of our program. We can either try and reduce the latency of the components, that is essentially to say, let me try to improve my hardware, or I can try to find ways to increase the cache hit rate. And this could be done in a couple of different ways. Maybe you as a programmer can redesign the program to exhibit better locality, and therefore it will have high hit rate, or the hardware designer can come up with better replacement policies. So besides performance, we also care about the area overhead of a cache. Now, what is the area overhead? Well, we know that a cache consumes area to store data. So the area that is used to store data is useful area in the sense that you're spending the area to store the information that you actually want to access. But the area that you're spending on tag is an overhead in the sense that they don't really store data, but that is essentially a metadata that is stored to get to the actual data that you want. So you could think of the tag array as an area overhead in the cache. So now the question is, how big is this overhead? So for this example that we talked, let's say that each data is the size of a word, and let's assume that it's a 64-bit ISA. So if it's a 64-bit ISA, each address is going to be of size 64 bits. And let's assume that each address is also going to store one word or 64 bits worth of data. So each row has 64 bits of tag for storing 64 bits of data. So that's almost like 1:1 ratio. So you're paying almost the same amount of overhead for as much overhead as the data size. That's a lot. And now if you go back to the example that we had before, and if you try to compute the overhead of this architecture, it is also quite significant. So the tag was 4 bits, and we said that the data is 1 byte. And notice that you also have another overhead for the valid bit, so that's another one additional bit. Now later on when we talk about how to implement LRU, you will notice that I also need extra bits to implement the LRU policy, but we are going to ignore that for now. Now in this architecture, for each row I have 5 bits of overhead to store 8 bits of useful data. So 5:8, and that is also not a great ratio if you think about in terms of the area overhead. So the bottom line is the area overhead of the architecture that we designed is quite significant. And the question is, could we reduce that overhead? So in the next lecture, we will be seeing how for the same tag, I can increase the amount of data that I'm going to be storing here so that I can reduce the number of tags that I need per byte of data.